Hi, my name is Natalie Leger, and I'm going to be explaining prokaryotic DNA replication, but cozy. Here is our prokaryotic double-stranded DNA represented with pink and red pipe cleaners. And here I am representing the beginning of replication. So helicase is an enzyme responsible for unwinding the double-stranded DNA, and I have it shown here as a piece of dark chocolate. Dark chocolate helps me unwind after a long day, so I thought it was an appropriate representation of this enzyme. And then we have the SSB, or single-stranded binding proteins, which hold single-stranded DNA open, keeping it from zipping back together during replication. Red wine stabilizes and supports me when I'm going through hard things, just like SSB does during DNA replication. And gyrase, shown here as a delicious donut wrapped around the double-stranded DNA. So gyrase is an enzyme that relieves torsional stress that occurs when DNA strands are separated and trying to supercoil. Donuts are obviously a huge stress reliever. So here, primase is an enzyme that adds RNA primers, which DNA polymerase III binds to, specifically on lagging strands where discontinuous replication is necessary. So primase is represented as knitting needles and yarn because knitting is one of the best cozy hobbies, and it is knitting on or adding primers shown as little blue socks onto the lagging DNA strand in red. So now let's talk about DNA polymerase III. DNA polymerase III is predominantly responsible for DNA replication, shown here on the leading strand in pink of DNA. It bound to the 3' OH group, available all the way at the free end of the leading strand, which it treats as a template strand. It then adds nucleotides to the newly synthesized anti-parallel strand shown in white. This follows the same direction of helicase, as well as the direction of replication represented as the most top arrow. Okay, so now on the lagging strand, in red, it finds its 3' OH group on the pre-added primers, where it treats the lagging strand as a template strand and begins synthesizing again more anti-parallel strands in white in short bursts. So these short bursts are going to create Okazaki fragments. And these Okazaki fragments needs to have their primers removed, which is done by DNA polymerase I, which goes behind DNA polymerase III, removing the primers and replacing them with DNA or sucking up the primers as a vacuum would. So all that's left to do is fill in the leftover gaps, or nicks, between the Okazaki fragments with more DNA. I use coffee here to represent ligase because coffee fills up the empty hole in my heart, just like ligase fills in the nicks. Thank you very much for watching about DNA replication. Here are my references.